If you recall what an exponential function is, it's y equals a to the x. And if one were to graph it, it has a horizontal asymptote at y equals 0. And it looks something like this, where it crosses the y-axis at 1. That's what we learned earlier in this chapter. As we continue in this chapter, the whole point of it is to learn some new things, and those new things are logarithmic functions. A logarithmic function is the inverse of an exponential function. These two functions are inverses. Does anybody recall how a function and its inverse are related as far as their graphs go? A function and its inverse are symmetrical with respect to each other about the line y equals x. So if this above graph here is an exponential function, a logarithmic function looks like the following. The horizontal asymptote becomes a vertical asymptote at x equals 0. And instead of crossing the y-axis at 1, it crosses the x-axis at 1. So what you see here is the basic shape of a logarithmic function. The whole point of logarithms, the reason that they exist, is to be able to solve an equation in which the variable is an exponent. At this point in your life, you've never solved an equation where the variable was an exponent. The variable had always been a coefficient, or it had been a denominator, numerator. So here's the definition of logarithmic function: a function in the form of y equals log base a of x. This is read once again, y equals log base a, that's this little guy right here, is called base, and you say of x. What this x is called one moment. This is called the argument. Are there two e's in argument? Of course there isn't. I know all things when it comes to spelling.
Wait, yeah. Together. I thought you meant together.
Now you're just making fun of me. I knew argue had an e, but I thought maybe put the men on it, it goes out. I'm a terrible speller. Terrible. The y is called the exponent. I'm sorry, the y is called the logarithm. So looking further here into logarithm, the inverse of y equals a to the x is is x equals a to the y. To find an inverse, you just replace the x's with y and the y with x's. In the function x equals a to the y is called a logarithm. It is usually written in the form y equals log base a of x and is read y equals log base a of x. So what you should get out of that is what's most important there, and it's said again here later, is that these two things that I'm circling here in green are equivalent things. There's just different ways to write them. These two things here in green mean the same thing One is called logarithmic form, and the other is called exponential form. They're both referring to the same thing. So if we continue, we come down to the definition of a logarithmic function. This is the formal definition. The logarithmic function, y equals log base a of x, where a is bigger than 0 and a is not 1, is the inverse of the exponential function y equals a to the x, which is everything that I just said, basically all summed up. Therefore, y equals log base a of x if and only if x equals a to the y. So some things here that I want to point out that are not common sense. Notice on the first equation here that has logarithm in it, y is by itself. In exponential form, that is the exponent. Notice the argument that's in the first equation becomes the part that's by itself in the exponential equation. Both of those things I think that you'll find is difficult to grasp why they're going in those places. The only thing that is consistent with our terminology is the base. When you write a to the y, we say that a is the base. When we say log base a of x, we're saying a is the base. So the a is consistent. The base is going to stay the base. This is completely new to you. You're going to learn it at a slow pace, but once you understand this, you'll find that it is very, very simple. I promise you. The results on the tests for Chapter 11 are usually very good. Properties. Properties of logarithms. These are the same basic properties of the properties of exponents, because logarithms are really just exponents. Suppose m and n are positive numbers, b is a positive number other than 1, and p is any real number, then the following properties are true. The product property. Product property says that if you have log of a base, such as b, and your argument is a product, so this argument, m times n, is a product because it's being timesed, you could, if you wanted, if it made the problem simpler, you could break it into two different logarithms that you're adding together. One where you take the first thing that you're multiplying as your argument, and the second one that you take the second thing that you're multiplying as an argument. A little example here. Let's say that we had log base 7 of 7x. Using the product property, you could write this as log base 7 of 7 plus log base 7 of x. When you're multiplying with your arguments, you're allowed to break it into two separate logarithms. That's what this property allows you to do. The quotient property, quotient means division or fraction, says that if your argument is a fraction, such as m divided by n, you can break it into two separate arguments where you take the numerator's argument minus the denominator's. So example with some numbers in it. Say we have log base 10 of 8 over x. According to the quotient property, we can write this as log base 10 of 8 minus log base 10 of x. That is the quotient property. Next we have a power property, which says if your argument has an exponent, in this case our exponent for our argument is this p. It says that you're allowed to take that p and write it as a coefficient of the logarithm. You can just take it and you can just write it in front. Example. Say that we have log base 11 of 84 squared. We are allowed, using this property, the power property, to write this as 2 times log base 11 of 84. That is the power property. Next we have the power of equality property. If you have one logarithm on the one side of the equation and another logarithm on the right side and they have the same base, it's really important to note that they have the same base. If they're different bases, this does not work. You're allowed to then just say, well, the argument on the left equals the argument on the right. Example. Say that we have a log base e 24, and that's equal to a log base e of 2x. According to the property of equality, we can conclude from that that 24 equals 2x, which therefore that means x is going to be 12 if you were going to solve the equation. We have two identities. The first one says that if you have log base a, then your argument has the same base of a. Then that whole thing simplifies to whatever your exponent was for your argument. It's important, once again, that the base for your logarithm and the base for your argument have to be the same thing. If they are the same thing, then that whole thing just simplifies to your exponent. For example, log base 81 of your argument of 81 to the fourth, according to this identity, that just equals 4. Log ID number 2. If you have a base, such as a, and its exponent is a logarithm, such as log base a of x, if the base and the base are the same, which they are, then your answer is the argument. Hello, Mr. Huggins. Oh, that's okay, Mr. Huggins. We like it when you come in here. For some reason, when I think of you, I think of chocolate and sugar. Chocolate and sugar. Really? Wow. Mr. Huggins, I'm probably going to get in trouble. This is going on the internet right now, but shouldn't it be a woman doing the wings? I mean, no one makes wings like Mama, you know? I'm going to get fired. This is going on the internet, and I don't even care. So, example. Let's say that we had 37 to the log base 37 of 9. According to this identity, that just equals 9.